probability mass function. This is nothing but the discrete case, okay? These are PMF, this is also called PMF. So this is for the discrete random variable. This is for discrete random variable. And as I showed you here, right, this will give me the probability, okay? What will be the exact probability at a given value? This gives me probability mass function gives me, okay, the probability of a discrete random variable at a specific value x, whatever is the value. So it will give me the exact probability at any given value x. This is my probability mass function, okay? So generally the outcomes are countable here, so all these things will come with discrete, right? These are for countable outcomes. Now what will be, okay, so, and why do we call it a mass? Okay, so for example, if you see our head tail example, right? So let me plot the graph. For example, okay, toss a coin and count number of heads. So what was the probability of x equal to 0? This was 1 by 4, that is 0 heads. Okay. Similarly, p of x equal to 1, that was half. This was my tail. This is equal to head tail and tail head. And probability of getting both heads, this was again equal to 1 by 4. This is equal to head. And my omega sample space was head tail, tail head, and tail. So this is my thing. So if I plot it, this is my x, this is my PMF. Okay, so these are my values. This is 0, this is 1, this is 2, 1, 2, this is 1 by 4, half, 3 by 4, and 1. Say, or I can make it more broad because we don't have more than half, right? I can make it even broader. This is my 1 by 4 and this is my half. See, this point is 1 by 4, this point is half. So what will be my probability at 0? What will be the height of this? At 0, this is equal to 1 by 4. At 1, this is half. This is my length. And again at 2, this is 1 by 4. So generally when we plot it in using in the graph, we get histograms or bars. These are called bar graphs or histograms. So these are the values that we get: 1 by 4, half, and 1 by 4 for corresponding. So this is my PMF here. So I'm just plotting what will be my exact probability at any given value for this thing, for 0, 1, and 2. Now you can see that the probabilities are concentrated at any given point. There is no probability in the middle. There's nothing in the middle, the whole this thing area. So in discrete random variables, the mass of the probability, the whole mass is concentrated at one given point. The whole value is concentrated at one given point. That's why it's called mass. My probability mass function, because each point will have some mass. Okay, so because of this, it is called probability mass function. The probabilities are concentrated at discrete points. Probabilities are concentrated at discrete points or mass. This is the reason why we call it probability mass function. Okay, I hope the nomenclature is clear. Now let's see some key points around this also. Key points. What are my key points? Let me color it another color. Some key points. We know these things, but we will just formalize it, discuss it probably. Okay. So first thing is that probability at any given value must be non-negative. Okay. For at any given point, we cannot have probability as negative, right? So probability at any point must be non-negative. That means greater than or equal to 0. Probability of x equal to small x, capital X equal to, this is how it is denoted, is always non-negative, means greater than or equal to 0 for all x. This is symbol for all, mathematical symbol. That is the first key point. Probability cannot be 0, and that's what it is obvious. It cannot be. Probability can, the range is from 0 to 1. Second point, just good to know. Okay, sum of all probabilities will be 1. Probabilities is equal to 1. How will you write it? Sigma p of x equal to x is equal to 1. This is your summation sign, and you sum it up. You can see here, right? 1 by 4 plus half plus 1 by 4. If you sum the probability at 0, at 1 and 2, this will not exceed 1. That's the main rule. We know this, we just formalize it. And the third point will be, for any point where the random value, where the random variable, okay, well, for any value, any point where the random value is not defined, what will be the probability there? For example, what will be the probability of finding -1 heads, or what will be the probability of finding 5 heads in 2 tosses? That will be 0, right? So what does it mean? For any point where RV is not defined, random variable is not defined, the probability is equal to 0. So these are the 3 key points here. Okay, these are self-explanatory, and it is coming from the definition of probability itself. Okay, so we have seen this. Okay, and now if I have to find the CDF, if I have been given the CDF, if I'm given CDF, how to find PMF? It's very simple. If you have given the CDF, so if the PMF is equal to probability of x equal to x of I, this will be equal to my fx, x of I minus f of x at 1 point behind that, x minus 1. So this is my CDF, both of them. This is your PMF. The probability at any given point. For example, we were given this, right? The jump thing. Where is the jump? This example we have seen from here, right? Let me copy it and put it here again for you. So here, if I want, from this formula, if I want to find what is the probability at x equal to 1, so this I can find using probability of at x equal to 1 minus probability at x equal to 0. So what is the probability at x equal to 1 here? 3 by 4. Xi is 1 and xi minus 1 is 0, minus 1 by 4, that is equal to half. This is equal to the jump of CDF This is my CDF. From CDF we can get the PMF. PMF is the probability at any given point. PMF is the probability at any given point. At 1, this is the jump is equal to, this is my PMF, and CDF is the running total. Okay, running total. Sum it up, sum it up, sum it up. Simple. Okay, at 1 point PMF, the running total CDF. Okay, I hope PMF is clear.